A good day to you, grade 10 learners. Welcome to today's Physical Sciences lesson brought to you by the Gauteng Department of Education. My name is Ndabezinhle Dliwayo, and I hope I find you well. In our lesson today, we are starting on a new section that is under electricity and magnetism. And we're saying this is the section on electrostatics. It is a very, very broad topic. However, for this segment, we are going to focus on conservation of charge and charge quantization with the main aim of trying to deal with typical examination questions. So I urge you, as we go over this segment, have your calculators with you, a place where you're going to do your writing, to take down important notes. So can you please take part actively so that we can go through the work together? So we're saying at the end of the lesson, you should be able to state the principle of conservation of charge. I believe when you think of principle of conservation, you've met this in different places. Conservation. Now we're talking about the conservation of charge, right? And then we're saying you should also be able to apply the principle of conservation of charge using Q is equal to Q1 plus Q2 divided by 2, where we're saying our Q there stands for the charge of an object that is after a physical activity such as contact. Okay, so when we bring two bodies, one having a charge of Q1 and the other one having a charge of Q2, we're saying their sum there represents the net charge divided by 2. We shall use this in our calculations, and we're saying this is specifically for identical size objects. You shall see where we apply this formula. It's quite an interesting calculation. And then also you should be able to state the principle of charge quantization and apply the principle. So where we're saying your Q, that is the charge of an object, is equal to n that represents an integer number, that is a whole number, okay, multiplied by QE, which represents our elementary charge that is carried by your electron, that is negative 1,6 times 10 to the power negative 19. We shall see how we do the calculation as well. And as I said again there, remember, it is important that you have your calculator with you as we go over this section. And then also remember to state that like charges repel and opposite charges attract. I believe this one we are familiar with it. And last but not least, you should be able to explain how charged objects can attract uncharged insulators due to polarization of molecules inside your insulators. Right, so these are our objectives for our lesson, and we have to achieve them. And definitely, I believe we shall achieve them. Right, so what is our pre-knowledge? We want to talk about electrostatics. Okay, our pre-knowledge will start off with our everyday experiences. Okay, the moment you see lightning, I believe these days our lightning is so much around us. Lightning, think of the occasional shock when you touch the door handle. I believe all of us we have gone through these experiences, and we're saying these have to do with our topic for today, that is our electrostatics. Okay, and we're saying when you have that occasional shock, normally when you go through the carpet, there is friction that is occurring between your feet and the carpet. And what we're saying there, what is happening is during friction, when the atoms enter into friction, there is transfer of electrons. So if we are having transfer of electrons, remember, it means some of the atoms are going to gain electrons, while other atoms will lose electrons. And what are we going to have after that? We're going to have an imbalance of charge. The situation where you go through the carpet, electrons are transferred into your body, right? And then you are now creating an imbalance of charge. Now you're having excess of electrons. And what happens now? You touch the knob of the door, and you're going to have a current of electrons that is going to flow from your body up to the door knob. And we're saying that flow of electrons is the one that you feel now as the shock. Okay, and so we're saying at large scale, you think of lightning. Okay, so when the lightning strikes, it's also a discharge or a current of electrons due to an imbalance which came about as a result of what? Of friction. All right. I hope you remember these experiences, and you have noted that even when you have the crackling sound, especially when it is cold. Okay, when it is cold, you experience these things. When you are removing your jersey, you hear that crackling sound, and when you are in a dark room, you can even see the sparks there. And we're saying all these, they fall under our section on electrostatics, right? So in our day-to-day experiences, again, our electrostatics, it finds application in different places, in instruments like the photocopiers. I hope you knew that. Laser printers, some paint sprayers, they apply our electrostatics, even in dust precipitators. All right. So this is the knowledge that you should have when you're coming into this lesson. Just some background knowledge on what we are dealing with. And remember, we're saying all matter is made up of our atoms. And inside our atoms, we have the two types of charge. That is the positive and the negative charges. The positive carried by our protons, and we're saying the negative charge carried by our electrons. I hope here I'm just refreshing your mind, you remember these things. And we're saying whenever we have an equal number of positive charges and negative charges, we have a neutral object. Okay, but however, when we have the transfer of electrons, remember what always moves are the electrons, not the protons. What is transferred are the what? Are the electrons. So whenever we have the transfer or the gain of electrons, an object becomes charged. If an object has equal number of charges of positive and negative, we're saying our object is neutral. Okay, can we remember these points as we go through our lesson? And therefore, when you look at a positively charged body, we're saying in a positively charged body, there are less electrons than protons. When you look at that image there, we can count how many positives do we have. 1, 2, 3, 4, 5, 6, 7, 8 positives. Okay, let's put it there. Plus 8 positives. And how many negatives? 1, 2, 3, 4, 5, 6. So we have negative 6. This has a positive charge, a charge of plus 2. Less electrons than protons. That gives us a positive charge. And therefore, we're saying if an object has a positive charge, it is electron deficient. Right? I hope you know these concepts. And then when we have a negatively charged object, you are saying if an object is negatively charged, it has more electrons than protons. And again, here we can count how many protons? 1, 2, 3, 4, 5, 6. That gives us plus 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a negative 9 overall. That gives us negative 3. Okay, so if something has a negative charge, it means an excess of electrons. And then we're saying, in our concept of electrostatics, we're saying, if objects have opposite charges, there are forces that exist between charged objects, okay? And the forces that exist between our charged objects, they can be repulsive forces or they can be attractive forces, right? So the objects that have opposite charges, like the negatively charged and the positively charged objects, they experience attractive forces. I hope we remember that, we know that. And then objects with the same charges, they experience repulsive forces. But always also remember that if you bring a charged object close to a neutral object, you can still experience attraction as a result of polarization. I hope you remember that concept of polarization. Right. So I was saying all this information that we are talking about in our pre-knowledge is part of our section on electrostatics. And I hope you remember those sections. And as I said, in our lesson for today, we want to focus on the conservation of charge and charge quantization. And as I said again, we're going to be dealing with typical examination questions that deal with so much of calculations. So let's have our calculators ready and let's be geared to start our lesson. Right. Now, as usual, we're going to start with the baseline assessment. Now, for this part of your assessment, I'm going to give you 3 minutes. Right. Welcome back. Welcome back. I'm sure that we are done there. Remember, as the lesson progresses, you can join us on our WhatsApp platform on 079 578 2908. So you can send your challenges there, even the solutions of the problems that we are actually dealing with. Okay, now let us look at the question. We're saying a neutral plastic ruler becomes charged when it is rubbed with a woolen cloth. After rubbing, the ruler has a charge of a negative 3,5 times 10 to the power negative 15 coulombs. Now distinguish between a neutral object and a charged. object. So what did we say? Number one, a neutral object has equal number of protons and electrons, equal positives and negative charges. And then how about a charged object? A charged object has either gained or lost electrons, right? And therefore it tends to have an overall charge. Now, looking at the ruler there, does the ruler gain or lose the electrons? Okay, so always remember that if an object has a negative charge, we said a negative charge means an excess of electrons. So since your ruler has a negative charge there, it means it gained your electrons. Okay, an object, if it loses electrons, it becomes positively charged. Fewer electrons than protons results in a positive charge. All right, and then if it gains, it has excess electrons, resulting in a negative charge. Right, I believe that part is done. Okay, let's go to the second part of our baseline. Right, so this is the last part of our baseline for today. I'm going to give you 4 minutes for this part. Right, welcome back. Welcome back. I hope you were able to attempt that question. All right. Remember, our ruler there, the charge there, it had a negative charge, and our pieces of paper there, we are saying they are actually neutral. So, how does the ruler now attract the paper? Well, we know that it is the opposite charges that attract. So remember, when your ruler is brought close to your pieces of paper, okay, the negative charges there, which are on the paper, are going to be repelled. Okay, and that is our process known as polarization. That is the separation of charges. We are creating regions in the paper that are actually partially positive and others partially negative. So what is going to happen is the side that is closest to the ruler is going to remain slightly positive there. Okay, and when we have that slightly positive charge on our paper with a negative ruler there, we're going to have our attraction, right? So this is serving to explain that the charged objects can attract neutral insulators, okay? By what? By the process of polarization. Okay, so when we're talking of the polarization, they were just saying it is just the separation of the positive and the negative charges. Okay, I hope that is making sense there. And then name one application of electrostatics in our daily life. In our daily lives, you can mention any of the following: in photocopiers, spray painting, fingerprinting, and so on. These are the places where we find application of our electrostatics. Okay, right. So remember we said this section on electrostatics is quite broad. However, our lesson today, we want to commit it to conservation of charge. So all these aspects that we mentioned in our baseline, I hope you understand them and you got some points there. So now we want to look at the conservation of charge. So we start by the principle of conservation of charge. So please, can you take down this principle? Right, when we're looking at the conservation of charge, we are saying that the net charge, take note of these keywords, the net charge of an isolated system remains constant during any physical process. Okay, a typical physical process is whereby we can bring the two charged objects to contact and then separate them. Okay, then we have these two key terms that I underlined there, the net charge, right? So when we're talking of the net charge, we're just talking about the sum of the two charged objects. We are going to look at typical examples as our lesson progresses. So if I bring body 1 with a certain charge and bring body 2 with a certain charge, okay, I'm saying the sum of their charges is what we call net charge. So it's simply addition there. That is what gives you the net charge. And then we talk of an isolated system, right? An isolated system is a system that does not allow the entry and exit of matter into the system, all right? So our system now is totally divorced from influence from the environment, okay? No matter can enter, no matter can go out. So it means no charges can come from outside, no charges can also escape, right? So it states that the net charge of an isolated system is conserved or is constant, right? So let's look at these two objects there. We have a rod, okay, with a charge of +4, right? I'll call that +4 Q1 there, right? And then we have there that cylindrical, that sphere with a charge, I'll call it Q2 with a charge of 0. Okay, so we're saying the net charge of these two, if this is an isolated system, their net charge, which I'll call Q, will be equal to the sum, that is Q1 plus Q2. Okay, so that will be +4 plus 0. Okay, and that gives us a net charge of +4. Take note of that. And now we're saying, since this system is isolated, okay, we bring them to contact, they touch each other, electrons are transferred, right? Let's see what is going to happen after that. Okay, let's look at the rod there. Now its charge is +2, okay? And the charge there of our sphere is now also +2, right? So this is our Q1, that is our Q2. Let's calculate their net charge after they come into contact and we separate them. So their net charge is still Q1 plus Q2. It is still the sum of their charges after contact. So we're going to have our Q1 is +2, okay? And then our Q2 is also +2. So we're adding them together there, and we're still getting an overall charge of +4. So this is what we mean by the conservation of charge in isolated system. So remember, when we're saying the net charge is just the sum of the charges on your bodies. I hope that makes sense. Okay, so let us proceed with our principle of conservation of charge. Right, so now if you are dealing with conductors, two conducting materials, remember, a conductor is going to allow electrons to move through them, isn't it? So now if we bring two conductors and they touch each other, okay, they are going to share the charges that they have. They are going to share their net charge. Okay, take note of this. If I bring a positively charged conductor to a negatively charged conductor, which one has excess electrons? Let's remember, excess electrons is the one that is negative, isn't it? Positive is a deficiency of electrons. So they touch each other. The electrons are going to move from where they are more, that is from the negatively charged conductor to the positively charged what? Conductor. Right. And what is happening in the process there? The net charge, remember the net charge, it is the sum of their charges. They are trying to share their net charge. Okay. Remember, when we're talking about the net charge, it is the extra, it can be the extra positive or the extra negative charges. Right. Those extra charges are going to be evenly distributed between the two conductors. That is, if they are identical. Right? Is that making sense? We shall do practical calculations pertaining to that. So they will share the net charge. And the reason for them to share, they are distributing the net charge over a bigger area because it's now in two surfaces, okay, surfaces of two different conductors. Then they distribute that charge. And the purpose of that, it is to minimize repulsion. Okay, I hope that is making sense. So now, if we were to bring two conductors together, one with a charge of Q1 and the other one with a charge of Q2, okay, it means what will be their net charge? Their net charge is their sum, that is Q1 plus Q2. We agree there, isn't it? And then we're saying electrons are going to flow from where they are more to where they are less, isn't it? After that, we have an even distribution of the net charge. It means what will be the new charge on each sphere? The new charge on each sphere now is going to be the average of the net charge, provided that your spheres are identical or equal. So if I bring two spheres that are identical, I add their charges together, okay, I get my net charge. Divided by 2, I'll get the new charge on each sphere after separation. Right? I hope it's making sense. If it is not, we will make it make sense by looking at a typical question. All right. And then think of insulators. If we were to bring together insulating materials, the electrons are tightly held in insulators. Okay, if they touch each other, nothing is going to happen. Electrons are not free to move in insulating materials. Remember, our insulating materials, they do not allow the flow of charge. Okay, I hope this is making sense. At the moment, let's grasp this formula. We use it to calculate our new charge on a single sphere after contact. Right, let's look at a typical example. Remember we said we want to do some calculations, so have your calculators ready. Let's go over the question together and you follow through how we do the calculation. All right, so now we have two identical metal spheres, A and B, on an insulated surface. Okay, they carry charges of negative 2,8 times 10 to the power negative 9 coulombs. I hope you still remember that the charge on the unit, the SI unit of charge is our coulomb, right? Right. And plus 4,5 times 10 to the power negative 9 coulombs, respectively, right? As we can see there in the diagram. Okay, calculate the new charge on each sphere after they moved apart. So A is negative, B is positive, they touch each other. We know that electrons will flow from A to B because our A is negative. All right, and we're saying these are identical. It means they will share their net charge equally. That is why we divide by 2. So what will be the new charge? Our formula, remember, it's the formula first. Our new charge, which we say Q, will be equal to Q1, let's call it QA, the charge for A, plus our QB. I hope you're taking down this calculation. Right, divided by 2. That will be the new charge on each sphere. All right, so let's substitute there. What is our QA? That is the charge on our A. Negative 2,8 multiplied by 10 to the power negative 9. We're adding what? 4,5 times 10 to the power negative 9. And then dividing that by 2. So you see, the important thing is just your formula there. You punch in those values into your calculator. What are we going to get? Can you punch in? I'm sure you get positive 8,5 times 10 to the power negative 10 coulombs. Right. So that is how we simply get the new charge on each sphere. So in other words, if you're dealing with identical objects, the new charge is going to be the average of the net charge because the net charge will be evenly distributed between your objects. Right. I hope that makes sense. Okay. Another reminder, remember when you are dealing with the charges, the units there, if you have 10 to the power negative 9, what unit, how do we often refer to it? Okay, remember we often refer to those as nano coulombs, NC there, meaning that the negative 2,8, we could have written it as negative 2,8 what? Nano coulombs. So remember, your nano coulomb is actually to the power of what? Negative 9. So this is how we are expected to do our calculation there. Right. I hope you have noted the steps. So your formula first, and then you do your calculation. Right. Having done that, now let me give you a small activity. This is on what we've covered so far up to this point. And take note, these are typical examination questions. So let's see how you're going to do on this one. I'm going to give you 5 minutes to tackle this question. Right, welcome back. Welcome back. Remember, you can send your solutions on 079 578 2908. Okay, let's look at the question. State the principle of conservation of charge. Remember, you just need to internalize that principle just for you to remember it. The net charge of an isolated system is what? Is always conserved in any physical process. And then we're saying which sphere loses electrons when the two spheres come to contact. So you remember, you just look at negative means excess electrons. Positive means deficiency of what? Electrons, fewer electrons than protons. So the electrons will move from where they are more to where they are less. So the one that is going to lose our electrons is our sphere P. So just look at the charge and then you are fine. And then the last part there, our calculation. Calculate the final charge on our sphere. I hope there you were able to recall that our nanocoulomb, we said our nanocoulomb is now to the magnitude of 10 to the power negative 9. So our final charge, how do we get the final charge after they are separated? Your formula, remember we said your Q, which is the final charge, okay, is the net charge, that is QA plus your QP divided by 2. And then you take the values as they are. Your A is 4,4 times 10 to the power negative 9. And then you are adding it to the negative 2 times 10 to the power negative 9. And we are dividing that by 2. Right? And then you put that into your calculator and you're going to get a positive 1,2 times 10 to the power negative 9 coulombs. Right? Okay, in the event that you have forgotten what this NC means, what this NC, and you start scratching your head, I can't remember, nanocoulomb, what does it mean? You can do your calculation there using the values as they are. Okay, let's see this. This is one way you can try to rob yourself out of your misery. Okay, so your QA, let's do this. You substitute there. What is my QA? You say 4,4, right? And then my QB, I'm adding them negative 2, okay, divided by 2. Right, when you do your math there, you're going to get a positive 1,2. And what will you do? Your answer there, to complete it as the appropriate units, you put that NC, whatever it stands for, and then you know I've done it, the nanocoulombs. Okay, because this and that are the same thing. Right, but practice, remember what nanocoulomb stands for, what microcoulomb stands for and looks like, so that you can actually attempt such questions. Right, so these are the questions that we are dealing with when it comes to our conservation of charge. So remember, our charge moves from where it is excess, that is, it's the electrons only that are moving, okay? And then we're saying they are evenly, the net charge is going to be evenly distributed. The main reason for that is to minimize the repulsive forces between our spheres there. Right. Now, the next aspect that we'll want to look at is the principle of charge quantization. Right, the principle of charge quantization. Right, we're saying the basic unit or the building unit of our charge is called the elementary charge. Okay, and this is the amount of charge that is carried by our single electron. Okay, and now we're saying, what is that unit of charge? How much charge is carried by a single electron? A single electron carries a charge of negative 1,6 times 10 to the power negative 19 coulomb. That is the amount of charge carried by a single electron. So now, suppose you are given a certain value of charge. Okay, what does that mean? Remember, our charge, we represent it by using our Q there. Our Q there is standing for our charge. This is our charge. Okay, it means that by looking at our principle of charge quantization, we're saying that if an object is a certain amount of charge, that charge translates to a certain number of electrons, which we call N. Okay, that is an integer number or a whole number of electrons. Remember, we're saying our electrons are the ones which are transferred or gained. As they move, each electron is carrying that amount of charge, which we denote by our QE there, which is our elementary charge. So your electron is going to be carrying a charge of negative 1,6 times 10 to the power negative 19 coulombs. All right, so we're saying a certain amount of charge, it is indicative of the number of electrons, and you multiply them by the charge carried by a single electron, and that gives you the overall charge that can be possessed by an object. So if an object has an overall negative charge, okay, you can actually get the number of electrons that are present in that particular object. How can we get the number of electrons there? We make n there the subject of our formula. We're saying the number of electrons is going to be equal to the charge, which is Q, divided by our QE. That will give us our number of electrons in a particular object with a particular charge. Is that making sense? I hope that is making sense. All right, let's look at a typical question so that we can see what we are dealing with. Right, an object has an excess charge of negative 4,8 times 10 to the power negative 9 coulombs. Okay, already you are knowing that that charge is the charge carried by a certain number of electrons, right? How many excess electrons is this? Okay, so remember, each electron carrying negative 1,6 times 10 to the power negative 19. So how many electrons is that? So the first step is our formula. The number of electrons is the charge, the excess charge there, divided by our elementary charge. That is the charge carried by our single electron. Okay, so you substitute there. There is your charge, and there is our elementary charge. Remember this value, negative 1,6 times 10 to the power negative 19. And this will give us 3 times 10 to the power 10 electrons. Okay, I hope that is making sense. Right, let's look at a different kind of example, and we see how we can still apply this formula of our charge quantization. Now we have two identical metal spheres on insulating stands. They have different charges. There's a charge of negative 4,8 times 10 to the power negative 18 coulombs, and then sphere 2 has 30 excess protons. Remember, our protons are positively what? Charged. So it means the charge carried by a single proton will be what? Plus 1,6 times 10 to the power negative 19 coulombs. Okay, now if the two spheres are brought into contact and then separated, what charge will each have? Okay, excess electrons or protons that this correspond to. So the first step, remember, if we want to get our new charge after contact, our formula, we know that our formula states that Q is equal to our Q1 plus our Q2 divided by 2. Right, we go to our question there. We say, what is our Q1? The charge on sphere 1, there we know it. Our Q1 is negative 4,8 times 10 to the power negative 18 coulombs. How about our Q2, the charge on sphere 2? You're told sphere 2 has 30 excess protons. So how much charge does that translate to? Right, so our Q2, we're using our formula NQE. So now N is the number of our protons, that is 30 protons, multiplied by the charge carried by a single proton, isn't it? We say that is a positive 1,6 times 10 to the power negative 19 coulombs. And then you can punch in that value into your calculator, and you are going to get a positive 4,8 times 10 to the power negative 18 coulombs, right? So this is our Q2, that is our Q1. Now we can substitute into our formula and do our calculation. Our Q1 negative 4,8 times 10 to the power negative 18 plus our Q2 is a positive, so it's 4,8 times 10 to the power negative 18. And you can see these are equal but opposite already. They're divided by 2. So this definitely gives us 0 coulombs. Right? So now it means the overall charge after separation, the charge on each of these spheres is going to be 0 coulomb, 0 coulomb. And then we're saying how many excess electrons or protons does this correspond to? 0 means neutral. Remember, this is no overall charge. Equal number of protons, equal number of electrons. So this means there are no excess electrons or protons because the two are now neutral. Okay, I hope that is making sense. So remember how we apply our formula there for our principle of charge quantization. Right, that being said, let me give you a small activity pertaining to that. This activity is also in two parts. So for the first part, I'm going to give you 4 minutes. Right, welcome back. Welcome back. Now let us look at the question together then. So we have two identical spheres, X and Y, as we can see there. They're suspended by threads from a ceiling. Now they are held at small distance apart as shown there. You can see our X is positive, our Y is negative. Now sphere X carries a charge of a positive 4 times 10 to the power negative 18, while sphere Y has an excess of 30 electrons. Right. So the first part, calculate the magnitude of the charge on sphere Y. So how do we get the charge on sphere Y? We're told this has got 30 excess electrons. Right. So what formula do we use to get our charge? Remember, we're saying our charge Q is equal to NQE. And your QE there, remember, is the elementary charge carried by our single electron. Okay, and therefore we're saying it's 30 electrons, that is your N. Okay, and then the charge by an electron is negative 1,6 times 10 to the power negative 19. And you get your value there, negative 4,8 times 10 to the power negative 18 coulombs. Right, I'm sure you're able to get that. And then give a reason why sphere X and Y move towards each other. What can you take note of there? The charges, okay, they have opposite charges, and we know that opposite charges, what? They attract. And I'm definitely sure that you were able to do that calculation. Right, a one last final calculation there. Right, for this one, I'm going to give you just 2 minutes for you to do this calculation. It's still the same question that is continued. Just 2 minutes. Can you work on this question? 2 minutes. Right, welcome back. Okay, so there you expected to calculate the charge on each sphere after they have separated. Remember there we calculated the charge for our sphere Y. It was actually a negative 4,8 times 10 to the power negative 18. Remember from your part 1, 2. So importantly is your formula there. Okay, you have your Q1 there, and that one is your Q2. So you just substitute into our formula there, your Q1 and your Q2, and you do your maths using your calculator there, and we get a negative 4 times 10 to the power negative 19. I'm definitely sure that you were able to do that calculation. Now that marks the end of our lesson for today. And as usual, I'm going to leave you with some homework. I'll give you a minute for you to take down these questions. Right, welcome back. Welcome back. Remember what we learned today? We spoke about the conservation of charge. We were saying the net charge of an isolated system is conserved or is actually constant during any physical process. And we say the conductors, they allow the electrons to actually flow through them, but the insulators, on the other hand, they do not allow the charges to flow through them. And importantly, remember, if you want to calculate the new charge on two identical spheres after contact, the new charge is going to be the net charge divided by 2. That is the sum of the charges divided by 2. Remember, our units are in coulombs. And then also we said, due to charge quantization, we're saying the charge on any system is equal to an integer multiple, okay, of the elementary charge. So that represents the number of your particles. It can be protons or electrons multiplied by the elementary charge, which is a plus or minus 1,6 times 10 to the power negative 19 coulombs. And last but not least, what we know is that our conductors, they allow charges to move while the insulators do not. Right, I hope you found the lesson quite informative. Till we meet again, may God bless you.